Space might be finite, immeasurable. Volume, but it has no edge, no end in. The way you're imagining it. Imagine a bug, a tiny flat bug living on the surface of a ball. This bug can only perceive two dimensions. It can move forward, backward, left, right, but it has no concept of up or down for this. Bug, the surface of the ball is the entire universe. There's nothing else. Now, does this bug's universe have an edge? No. The bug can walk in any direction forever and it will never hit a wall, never fall off, never reach a sign that says end of space. But wait, is the bug's universe infinite? Also, no. The surface of a ball has a definite size. It's measurable. It's finite. So, how can something be finite but have no edge? Here's the secret. The surface curves. It wraps around. If the bug walks in a straight line long enough, it ends up exactly where it started without ever turning around. The bug circumnavigates its entire universe just by going straight. Finite but unbounded, limited size, but no boundary. That's the key. Now, here's where it gets interesting. The bug can actually discover that its space is curved without ever leaving it, without ever floating up into the third dimension and looking down at the ball. The bug can figure it out from within. How? By doing geometry, by measuring things carefully. Now, here's where it gets interesting. The bug can actually discover that its space is curved without ever leaving it, without ever floating up into the third dimension, and looking down at the ball. The bug can figure it out from within. How? By doing geometry, by measuring things carefully. Let me show you what I mean. On a flat surface, if you draw a triangle and measure all three angles, they always add up to exactly 180. Always, every triangle, no exceptions. But on a curved surface like a sphere, the angles add up to more than 180. The triangle is fatter than it should be. On a flat surface, if you draw a circle and measure the circumference, it's always a little more than 6 times the radius. That's just how circles work. But on a sphere, the circumference is less than you'd expect. The surface curves, so the circle pinches. The bug can do these measurements. The bug can discover through careful geometry that something is wrong with its space, that the rules don't work the way they should. That space itself is curved. And here's the beautiful part. The bug does this without ever leaving its universe, without ever seeing it from the outside. The curvature is intrinsic. It's built into the fabric of space itself. Our universe might be exactly like that. We might be the bugs. Einstein told us that. Space is curved, not metaphorically, not as a mathematical trick, actually. Physically curved. The fabric of space, the void between stars, the emptiness. You're sitting in right now, it bends. And what causes the bending? Mass, matter, energy. Every star curves space. Every planet curves space. Even you curve space just a tiny bit. The more mass of something is, the more it warps the space around it. So here's the picture. Our three-dimensional space might curve in a fourth dimension that we can't perceive directly, just like the bug's two-dimensional surface curves. In the third dimension, we can't see the curvature by looking at it, but we can detect it, we can measure it, and if our space curves enough, if it curves all the way around, then it closes on itself like the surface of a sphere. But in 3 dimensions, what would that mean? It would mean the universe is finite, it has a definite size, a measurable volume, but it would also mean the universe has no edge, no boundary, no wall. If you got in a spaceship and flew in a perfectly straight line, just kept going and going, for billions of years you wouldn't hit a wall, you wouldn't fall off an edge, you wouldn't reach the end, you'd end up back where you started. Here's the truth. The universe might be finite, but unbounded, limited, but edgeless. It might have a size, but no border. And this answers the question everyone asks, the question that keeps people up at night. What's outside the universe? Nothing. Not empty space, not darkness, not some other realm, nothing. Because outside doesn't exist. Think about it. What's outside the bug's universe? What's outside the surface of the sphere? From the bug's perspective, the question makes no sense. The surface is everything. There is no outside. For us, it might be the same. Space-time is everything. There is no outside. The question assumes something that doesn't exist. And now comes the shock. This isn't just philosophy. This isn't just speculation. We can test it. We are testing it. Remember how the bug could detect curvature by measuring triangles and circles. We can do the same thing on a cosmic scale. We can look at the largest structures in the universe. We can measure the angles of giant triangles formed by distant galaxies. We can check if the geometry works out the way it should for flat space. And what do we find? So far, the universe looks very close to flat on large scales. Very close. But very close doesn't mean exactly flat. There could be a tiny curvature that we haven't detected yet, a slight curve that would only show up at scales larger than we can currently measure. If the universe is positively curved like a sphere, then it's finite and closed. You travel far enough, you come back home. If the universe is negatively curved like a saddle, then it's infinite and open. It goes on forever in every direction. If the universe is perfectly flat, then it's also infinite. Space just keeps going, with no end. But here's what we know for certain. Whether the universe is finite or infinite, it doesn't have an edge. It doesn't have a wall. There's no boundary. You can reach where space just stops. Either it goes on forever or it wraps around on itself. Those are the options. Edge of the universe isn't one of them. Let me say that again because it's important. Space doesn't end either. It's infinite and keeps going, or it's finite and loops back. But there's no wall, no border, no end in the way your brain wants there to be. The universe is not a room. It's not a box. It's not contained inside something larger. The universe is everything, and outside is not a place that outside might not exist. You might be wondering, okay, space is curved, but curved into what? If the bug surface is curved in three-dimensional space, then our three-dimensional space must be curved in what? A fourth dimension. And here's where we have to be careful. We don't need a higher dimension for space to be curved. The curvature is intrinsic. It's a property of space itself, measurable from within without reference to anything outside. Let me explain what I mean. When we say the bug's universe is curved, we're describing it from the outside. We see the ball. We see the surface wrapping around. But the bug doesn't see any of that. The bug just notices that geometry doesn't work. Right? Triangles are weird. Circles are weird. Something is off. The bug discovers curvature through measurement, not through seeing a higher dimension. We're in the same situation. We can measure the curvature of our space without needing to see it from a fourth dimension. We just do geometry on large scales and check if the results match, flat geometry or not. Here's the key. Curvature is not about bending into something. Curvature is about geometry, being different than expected. That's the definition. A curved space is a space where the rules of flat geometry don't apply. So stop trying to visualize the universe as a balloon floating in some larger space. That image is misleading. There's no larger space. There's just our space with its own intrinsic geometry, which might be curved. Now, let's talk about something else, because curvature isn't the only strange thing about space. Einstein told us something even more remarkable. Space and time are connected. They're woven together into a single fabric called space-time. And when we talk about the curvature of the universe, we're really talking about the curvature of space-time. This matters because it changes everything. Here's an example. You probably know that time passes at different rates depending on where you are. A clock on a mountain runs slightly faster than a clock in a valley. A clock on a speeding airplane runs slightly slower than a clock on the ground. These aren't mechanical errors. These aren't problems with the clocks. Time itself runs at different rates in different places. And why? Because of curvature. Mass curves space-time. And when space-time is curved, time flows differently in different locations. Think about what this means. Near a massive object like the Earth, space-time is curved. And that curvature affects not just space, but time. Clocks tick slower near massive objects. Time literally passes more slowly. This has been measured. This is not speculation. Scientists have taken identical atomic clocks, put one on a plane and one on the ground, flown the plane around, and compared the clocks afterward. They're different by tiny amounts, but measurably different. The clock on the plane experienced slightly less time than the clock on the ground because it was higher up, further from Earth's mass, in a region where space-time is less curved. But wait, there's more. This curvature of space-time isn't just an interesting fact, it's the explanation for gravity. You were probably taught that gravity is a force, that the Earth pulls on you, that there's some invisible rope connecting you to the planet, yanking you downward. But that's not what's happening. Here's the truth. You're not being pulled down. You're following the natural path through curved space-time. Let me try to make this intuitive. Imagine you're in a spaceship, far from any planet or star, no gravity, you're floating. Now the spaceship starts accelerating, it fires its engines and speeds up. What happens to you? You get pressed against the back of the ship. You feel weight, you feel exactly like you would if you were standing on a planet. Einstein realized something profound. There's no way to tell the difference. If you're in a closed box and you feel weight, you cannot determine whether you're on a planet being pulled by gravity or in a spaceship that's accelerating. The experiences are identical. This is called the principle of equivalence. And it's the foundation of everything. Here's why it matters. If acceleration and gravity feel the same, then maybe they are the same. Maybe gravity isn't a force at all. Maybe what we call gravity is actually the effect of curve. Space-time. Think about it this way. When you drop a ball, it falls, you think gravity is pulling it down, but actually the ball is just following a straight line through curved space-time. That sounds crazy, right? How can falling be a straight line? Because in curved space-time, straight lines look curved from our perspective. The ball is taking the most natural path through space-time, the shortest path, the path that any free object would follow. We call these paths geodesics. And in flat space-time, geodesics are straight lines, but in curved space-time, geodesics look curved to us. They look like orbits, like falling, like the motion we associate with gravity. So the Earth isn't pulling you down. The Earth is curving the space-time around it. And you, by existing in that curved space-time, naturally move toward the Earth, not because of a force, but because of geometry. Now watch this. This explains something that puzzled scientists for centuries. Why do all objects fall at the same rate? A feather and a hammer in a vacuum hit the ground at the same time. Why? If gravity were a force, you'd expect heavier objects to experience more pull, but they also have more inertia, more resistance to acceleration. And these two effects exactly cancel. It seems like a coincidence, but in the curved space-time picture, it's not a coincidence at all. Objects aren't being pulled. They're following geodesics. And the geodesic doesn't care what the object is made of. A feather and a hammer follow the same curved path through space-time because the path is determined by the geometry, not by the object. Here's the secret. Gravity is not a force. Gravity is geometry. The curvature of space-time is what we experience as gravity. And this brings us back to the question of the universe. If mass curves space-time and the universe is full of mass, then the universe is full of curvature. Every star, every galaxy, every particle of matter contributes to the overall curvature of space-time. The total amount of matter and energy in the universe determines its overall shape, its geometry, whether it's curved like a sphere or curved like a saddle or perfectly flat. And that geometry determines the fate of the universe. If there's enough mass, space curves. Positively, the universe is closed. It's finite. And if you wait long enough, it might even collapse back on itself. A big crunch. If there's not enough mass, space curves negatively. The universe is open. It's infinite. It expands forever, getting colder and emptier. If there's exactly the right amount of mass, space is flat. The universe is infinite. It expands forever, but just barely right, on the edge between collapse and eternal expansion. Which one is our universe? We've measured it. We've looked at the cosmic background, radiation, the leftover glow from the Big Bang. We've studied the distribution of galaxies. We've calculated the total mass and energy. And the answer is our universe is very close to flat, remarkably close. So close that it's almost suspicious, but very close to. Flat leaves room for mystery. There, could be a tiny curvature we haven't detected. And even if it is perfectly flat, the question remains, why? Why? This particular geometry and not some other? Here's what we know for sure. Space is curved. Mass causes curvature. The geometry of the universe depends on what's in it. And that geometry determines whether the universe is finite or infinite, whether it has a shape that closes on itself or extends forever. The universe is not a fixed stage where things happen. The universe is a dynamic fabric that bends and warps and shapes itself according to its contents. And we're part of that fabric. We curve it, and it curves us. So let's bring this all together because we've covered a lot of ground, and I want to make sure the picture is clear. Space is curved. The universe might be finite, but without edges. There's no outside. Gravity isn't a force, but geometry. Mass tells space-ame how to curve, and curved space-time tells mass how to move. But there's one more thing we need to talk about, and it's the hardest part of all. Our intuition is wrong, completely, fundamentally, hopelessly wrong about all of this. And that's okay. Here's why. Your brain struggles with these ideas. You evolved on a small planet, moving at slow speeds, experiencing weak gravity your ancestors needed to throw spears at. Animals find ripe fruit, avoid predators they did not need to. Understand the curvature of space in me. So your brain built a model of reality that works for everyday life. A model where space is flat, where time flows at the same rate everywhere, where things fall because they're pulled by invisible forces, where everything is contained inside something larger. That model is wrong, but it works well enough for surviving on Earth. So evolution kept it. The problem comes when you try to. Think about the cosmos. You try to. Imagine the shape of the universe when you ask questions like, what's outside? Your brain uses its everyday model and gets nonsense answers. Here's the truth. The universe is not required to make sense to your intuition. The universe is required to be consistent with itself. And it is. The mathematics works. The predictions match observations. The theory holds together. It just doesn't feel right. And that's your problem, not the universe's problem. Now, let me address something that might be bothering you. If the universe could be finite and without edges, if it curves back on itself, what does that actually mean for us? What difference does it make? Well, here's one way to think about it. Imagine you're an astronaut. You get in the most advanced spaceship ever built. You pick a direction and you start flying perfectly straight, no turns, just forward forever. In an infinite universe, you fly forever and never return. Every moment takes you somewhere new. Space goes on without end. But in a finite curved universe, something strange happens. After billions of years of travel, the stars start to look familiar. The galaxies seem like ones you've passed before, and eventually you arrive back at Earth, right where you started. You circumnavigated the universe without ever turning around, just by going straight. That's what it means for space to be curved and closed. Straight lines become loops. Forward forever becomes back to the beginning. Now, practically speaking, this doesn't matter much for our daily lives. The universe is so large that even if it's finite, it's far too big for us to ever circum. We'll never build a ship fast enough or live long enough to complete the journey. But conceptually, it changes everything. It means the universe doesn't need an outside. It doesn't need a container. It doesn't need edges or walls or boundaries. It can be complete in itself, self-contained, everything that exists, existing within a structure that loops back and closes. Here's the key. The question, what's outside the universe, assumes a certain kind of universe. It assumes space is like a room contained inside something larger. But if space curves back on itself, that assumption is wrong. There is no outside. The question dissolves. It's not that we don't know the answer. It's that the question doesn't apply. You know what? People hate this answer. They really do. They want there to be an outside. They want there to be something more, something beyond. Their brains crave it. But the universe doesn't owe us satisfaction. The universe is what it is. And part of understanding physics is accepting that some questions are based on false premises. What's outside the universe might be one of those questions. Not a mystery we haven't solved yet, but a question that was never valid to begin with. Now watch this. There's something beautiful about this picture, something I don't want you to miss. We are tiny, unimaginably small compared to the cosmos. We live on a speck of dust orbiting an ordinary star in an ordinary galaxy among hundreds of billions of galaxies. And yet we figured this out. We, the bugs on the surface, discovered that our space is curved. We measured the geometry. We tested the predictions. We built a theory that explains gravity as curvature and describes the shape of the universe itself. We can't see the curvature directly. We can't float up into a higher dimension and look down, but we deduced it through mathematics, through careful measurement, through the power of human thought. That's remarkable. It's genuinely miraculous that creatures made of atoms can understand the fabric of spacing. That we can ask, what is the shape of everything, and actually make progress toward an answer. Let me leave you with something to think about. We don't know for certain if the universe is finite or infinite. We don't know if it curves back on itself or extends forever. The measurements are close to flat, but close isn't certain. What we do know is that the universe is far stranger than our intuition suggests. The space bends, time stretches, geometry depends on. What's in it? The cosmos might be a closed loop with no outside, or an infinite expanse with no end either. Way there's no wall, no edge, no boundary where space stops and something else begins. The universe is infinite with an end, or finite without edges, or infinite without edges, but never, never a box with walls. Here's the deepest part. When you look up at the night sky, you're not looking at objects scattered inside a giant room. You're looking at matter embedded in curved space-time. Every star, every galaxy is part of the fabric, and the fabric shapes itself around its contents. The universe isn't a container holding things. The universe is the things and the space between them, woven together, curving and flowing and existing as one unified structure. There is no outside because there is nothing but the universe. It is complete. It is whole. It is everything. I know this is hard to accept. I know your brain wants more, wants an answer that fits into familiar categories, wants to know what's beyond, but sometimes the deepest understanding comes from accepting that certain questions don't have the kind of answers we expect. That reality is structured differently than we imagined, that the universe is under no obligation to make intuitive sense. So what's outside the universe? Nothing. Not empty. Space, not darkness, not another. Universe. Nothing, because outside is not a concept that applies. The universe might be finite, it might be infinite, but either way, it's everything. And everything doesn't have an outside. That's not a failure of knowledge. That's a feature of reality. That's how the cosmos actually is. And we figured that out. Tiny creatures on a tiny planet looking up at the stars, doing geometry, testing predictions, pushing the boundaries of understanding.
This is what most schools are creating. A hold up the wind up robot, wind it up. Let it walk in circles, I wind it up. It follows its programming, does exactly what it's told, repeats the same pattern over and over. No deviation, no creativity, no thinking. A memorization machine Put down the robot, pick up the blocks. This is what we should be creating. Hey, start building something with the block C, open-ended, creative. Problem solving, experimenting, trying, failing, adjusting, building something that didn't exist before. A thinker? Hey, put down the blocks, look at audience A. Right now, our education system is mass producing the robot. Children who can recite facts, who can follow procedures, who can pass standardized tests, who can do exactly what they're told. But can they think? Can they solve new problems? Can they create? Can they adapt when the situation isn't what they've been programmed for? Add a pause, most of them can't. Because they've been trained to memorize, not to think. They've been turned into machines, not developed as thinkers. Of direct addressix. And if you're a parent, a teacher, or anyone who cares about the next generation, this should terrify you. Because the world doesn't need more memorization machines. We have actual machines for that. Computers that can store and retrieve information far better than any human. What the world needs, what your children need, is the ability to think, to reason, to solve problems that don't have predetermined answers, to create solutions that don't exist yet. Richard Feynman understood this deeply. He saw what the education system was doing to children, and he fought against it. He showed us how to raise thinkers instead of memorization machines. Today, I'm going to show you what he discovered. I'm going to show you what's broken and how we're educating children. And I'm going to show you how to fix it, how to raise thinkers. Real thinkers. Children who can actually use their minds instead of just storing information in them. Hey, walk across stage. Let me start with a story. This story changed how Feynman thought about education forever. And once you hear it, it'll change how you think about it too. It's the 1950s. Feynman's father takes him for walks in the woods. Young Richard, maybe 6, 7 years old, and his father teaches him about nature, but not the way other parents teach. Not by telling him facts. Not by making him memorize the names of birds and plants. Far share the method. Here's what Feynman's father does. They see a bird. And his father says, see that bird. Do you know what kind of bird that is? And young Richard says, no. And his father says, it's a brown-throated thrush. But in Germany, they call it a Hausenfugel. And in Chinese, they call it a chungling. And in Japanese, a katanotekta. No. His father says, you know what that bird is called in 4 different languages. But you still know absolutely nothing about the bird. You only know what different people call it. Continue the story. Then his father says, now let's look at what the bird actually does. See how it pecks at its feathers. Why do you think it does that? And they observe, they hypothesize, they think about it. Not memorizing names. Understanding behavior, thinking about why. Make the point, that's the difference. That's the entire difference between raising a thinker and creating a memorization machine. The memorization machine knows the bird is called a brown-throated thrush. That's what you're supposed to know for the test. That's what gets you the points. The thinker understands why the bird behaves the way it does, observes, questions, reasons, develops actual understanding of actual reality. A jumper get intensa, and here's what Feynman realized: most schools are teaching kids to memorize the names. This is a brown-throated thrush. This is mitochondria. This is the Pythagorean theorem. This is the capital of France. Names, labels, facts, information to be stored and retrieved. But they're not teaching kids to think about the bird, to understand mitochondria, to reason about why the Pythagorean theorem is true, to think about why Paris became France's capital. Or direct statement, they're creating memorization machines, not thinkers. And those memorization machines are completely unprepared for real life. Because real life doesn't ask you to recite facts. Real life presents you with novel problems that require actual thinking. Present the core issue. So let me show you exactly what's wrong. The specific ways our education system creates memorization machines instead of thinkers. Because once you see these, you can't unsee them. And you can start doing something different with your own children. First problem. Problem 1, we reward correct answers instead of good thinking. A child solves a math problem, gets the right answer, gets a gold star, gets an A, gets praise. Another child solves a math problem, gets the wrong answer, but shows creative thinking, tries a novel approach, demonstrates genuine reasoning even though it doesn't work, gets an F, gets correction, gets disappointment. What does this teach children? It teaches them what matters is the correct answer. How you think doesn't matter. The process doesn't matter. Only the result matters, so facts make the impact clear. So children learn to find the shortest path to the correct answer. Memorize the procedure. Follow the steps. Don't think creatively. Don't try novel approaches. Don't risk being wrong. Just produce the correct answer. That's what gets rewarded. If Falzer share Feynman example of Feynman told a story about this. He's talking to a child who's been taught that energy is something that makes things go. So Feynman asks, does a coiled spring have energy? And the child confidently says no, because it's not moving. The child has memorized that energy makes things go. So if something isn't going, it doesn't have energy. That's the logic. Ayers make the point, the child got the answer wrong. But was the child stupid? No. The child was thinking logically from what they'd been taught. The problem wasn't the child. The problem was the teaching. Teaching a definition without teaching understanding. Teaching words without teaching concepts. Creating a memorization machine instead of a thinker. Second problem, problem 2, we punish mistakes instead of treating them as learning. A child doesn't know something. Admits it. Says, I don't know. Gets marked wrong. Feels shame, learns not knowing is bad. A child tries to solve a problem. Makes a mistake. Gets it wrong. Gets corrected. Gets a bad grade. Learns making mistakes is bad. I get passionate. This is devastating. This is how you kill thinking. Because thinking requires not knowing. Thinking requires making mistakes. Thinking requires being wrong on the path to being right. But we punish all of that. We punish admission of ignorance. We punish errors. We punish the entire thinking process. Let's make the contrast. Thinkers aren't afraid of being wrong. Thinkers expect to be wrong initially. That's how thinking works. You start with an idea, you test it, it's wrong, you adjust. You try again. You're wrong differently, you adjust again. Eventually you're right. But memorization machines are terrified of being wrong because they've been trained that wrong is bad. Wrong is failure. Wrong is shameful. Share what this creates. So they don't think, they wait to be told the right answer. They memorize it, they repeat it, safe. No risk of being wrong, no thinking required. Share Feynman's approach, or Feynman loved being wrong. When someone proved him wrong, he'd get excited. Oh, I was thinking about this incorrectly. Now I can think about it better. Thank you for showing me where my thinking was flawed. A being wrong meant learning, meant improving, meant thinking was happening. Make the point that that's a thinker. Someone who sees mistakes as progress, as information, as necessary steps toward understanding. But our education system teaches the opposite. Teaches kids to avoid being wrong at all costs. Teaches them to stop thinking and start memorizing. Third problem, problem 3, we teach what to think instead of how to think. A child asks C, why is the sky blue? Most teachers say, because of Rayleigh scattering. The atmosphere scatters shorter wavelengths more than longer wavelengths. So blue light scatters more. The child memorizes this, repeats it on the test, gets an A. But does the child understand? Can the child reason about it? If you asked, why isn't the sky violet then? Could the child figure it out? No, because they memorized what to think. They weren't taught how to think about it. Acts show the alternative of Feynman's approach. Why do you think the sky is blue? What could cause that? Let's think about what we know. Light from the sun is white. So what could separate it into blue? What do we know about light and matter? What do we know about the atmosphere? Guide the thinking. Don't provide the answer. Make the child reason. Make them think through possibilities. Make them develop the mental muscles of reasoning. Make the distinction. Teaching what to think creates memorization machines. They know the answer, but they can't think about similar questions. They can't apply the reasoning to new situations. They can't figure anything out they haven't been told. Teaching how to think creates thinkers. They might not know this specific answer initially, but they can figure it out. They can reason about it. They can apply their thinking to any question. Fourth problems. Problem 4, we test memorization instead of testing understanding. Tests ask, what is the capital of France? What is the formula for photosynthesis? Who signed the Declaration of Independence? Questions that have one right answer. Questions that test whether you memorize the information. Questions that a computer could answer better than any human. Pause, but tests don't ask, why did Paris become the capital instead of another city? Why does photosynthesis work the way it does? What were the different arguments about signing the Declaration? Questions that require thinking, questions that test understanding, questions that reveal whether you can actually reason, that make the impact. So students optimize for the test. They memorize facts. They don't develop understanding. Why would they? Understanding isn't measured. Understanding doesn't improve your grade. Memorization improves your grade. So that's what they do. That's what we've trained them to do. Share Feynman's experience. Feynman served on California's Curriculum Commission, evaluating science textbooks, and he was horrified by what he found. Books full of facts, full of definitions, full of things to memorize, but almost nothing that taught kids how to think scientifically, how to observe, how to hypothesize, how to test, how to reason. To share his reaction, he gave a scathing report. He said these books teach children science, without teaching them anything about how science actually works. They teach what scientists have discovered without teaching how to think like a scientist. They create memorization machines who can recite scientific facts but can't think scientifically. Fifth problems. Problem 5. We prioritize coverage over depth. The curriculum must cover 40 topics this year, so you spend 1 week on each. Skim the surface. Move on. Can't go deep. No time. Too much to cover. Make the impact so children learn a little about everything and understand nothing deeply. They skim surfaces. They memorize key terms. They move on before developing real understanding. They become memorization machines who know a little bit about a lot of things, but can't think deeply about anything. If I can make the contrast, thinkers learn deeply. They take one thing, they explore it thoroughly. They understand it from multiple angles. They connect it to other things. They develop genuine understanding that transfers to other domains. Better to understand 3 things deeply than to memorize facts about 30 things. As share Feynman's approach, Feynman would spend months on a single physics concept, exploring it, playing with it, understanding it from every angle, building intuitions, creating mental models. Other physicists would cover more material faster. But Feynman's deep understanding meant he could solve problems they couldn't, could see connections they missed, could think in ways they couldn't. Make the point. Depth creates thinkers. Breadth creates memorization machines. We're choosing breadth. We're creating machines. Pause. Bring it together. So those are the 5 problems. We reward answers instead of thinking. We punish mistakes instead of treating them as learning. We teach what to think instead of how to think. We test memorization instead of understanding. We prioritize coverage over depth. These create direct address, and together these create memorization machines. Children who can recite, who can follow procedures, who can pass tests, but who can't think, can't reason, can't solve novel problems, can't create. Get hopeful. So how do we fix this? How do we raise thinkers instead of memorization machines? Let me show you Feynman's principles. The specific things you can do, as a parent, as a teacher, as anyone who influences children to develop thinking instead of memorization. Principle 1, reward the thinking process, not just correct answers. When a child solves a problem, don't just check if the answer is right. Ask, how did you figure that out? What did you think about? What did you try? Reward good thinking even if the answer is wrong. Praise creative approaches. Praise clear reasoning. Praise willingness to try novel methods. Make it concrete. You got the wrong answer, but I love how you thought about this. You tried something I've never seen before. That's excellent thinking. Let's figure out together where it went sideways. Versus wrong. Here's the right way to do it. Memorize this procedure. Share the impact are the first creates a thinker. Someone who values good thinking and isn't afraid to try. Someone who learns from mistakes. The second creates a memorization machine. Someone who learns to follow procedures and never deviates. Principle 2. Make mistakes safe and valuable. When a child doesn't know something, celebrate it. Excellent, something you don't know yet. That means you get to learn something. Let's figure this out together. When a child makes a mistake, treat it as data. Interesting, you thought X, but it's actually Y. Why do you think you thought X? What made sense about that? What can we learn from this? Make the mindset shift. Mistakes aren't failures. Mistakes are experiments that give you information. I don't know, isn't shameful. It's the starting point of learning. Create an environment where children aren't afraid to be wrong, where they're willing to try, where they learn from errors. Our share Feynman example, Feynman's father did this constantly. Young Richard would have an idea about how something worked, and his father would say, "That's interesting. What made you think that?"
Let's test it and see. Not.
That's wrong. But let's think about this together. I say make the impact that created a thinker. Someone comfortable with not knowing, comfortable with being wrong, comfortable with the process of figuring things out. Principle 3. Ask questions instead of providing answers. When a child asks, why, don't immediately give them the answer. Ask them, what do you think? Why do you think that happens? How could we figure that out? Make them think. Make them hypothesize. Make them reason. Guide their thinking. But don't do the thinking for them. Make it concrete to a child. Why do boats float? A bad response, because of buoyancy. Objects float when they displace water equal to their weight. Good response? Great question. Why do you think they float? What would make something float or sink? Let's think about this together. Share what this does to you. The bad response creates a memorization machine. The child memorizes buoyancy and displacement. Without understanding, the good response creates a thinker. The child reasons, observes, tests ideas, develops genuine understanding. Principle 40, Principle 4, focus on understanding, not coverage. Don't rush through topics. Go deep. Let children explore. Let them play with concepts. Let them understand thoroughly before moving on. Better to understand 3 things well than to memorize facts about 30 things. Make it practical. If your child is curious about how plants grow, don't give them a 5-minute lesson and move on. Spend a month on it. Plant seeds, observe daily. Experiment with different conditions. Draw pictures. Ask questions. Develop deep understanding. Share the payoff. That deep understanding of plants transfers. They learn about observation, about cause and effect, about patience, about experimentation, about systems. That's thinking. That transfers to everything. That's valuable. Principle 5, teach through experience and discovery, not lecture and memorization. Don't tell children facts to memorize. Create experiences where they discover principles themselves. And make it concrete. Don't say things fall down because of gravity. Instead, drop different objects. Let them observe. Ask, what do you notice? What's the pattern? Why do you think that happens? Let them discover that things fall. Let them notice the pattern. Then introduce the word gravity as a name for what they've already discovered. If I share Feynman's philosophy, Feynman said, what I cannot create, I do not understand. If a child memorizes that gravity makes things fall, they don't understand gravity. But if they discover through experience that things fall, and then learn that we call this gravity, they understand. They created the understanding through experience. It's real, it's permanent, it's usable. Share transformation story. Let me tell you about a family who applied these principles. Call them the Johnsons. Their daughter, Emma, was struggling in school. Good grades, she could memorize and regurgitate. But she wasn't actually learning, wasn't developing as a thinker. They pulled her out of traditional school, started homeschooling using Feynman's principles. Share their approach and no textbooks, no curriculum to cover, no memorization. Instead, Emma got curious about something and they'd explore it deeply. She wondered how bridges work. They'd spend weeks on bridges, visit bridges, build model bridges, experiment with structures, understand the principles thoroughly. She wondered how music works, months on music, learning an instrument, understanding sound waves, composing, experimenting. Share what happened in the first year. She learned about maybe 6 topics, deeply, thoroughly, with genuine understanding. A traditional school would have covered 60 topics, superficially, through memorization. The result of 5 years later, Emma is back in traditional school, and she's the best student, not because she memorized more, but because she learned how to think. When given a problem she's never seen before, she doesn't panic. She thinks about it, reasons about it, figures it out, because she's a thinker, not a memorization machine. I can make the universal point that that's what happens when you prioritize thinking over memorization. You create someone capable, someone who can handle the unknown, someone who can actually use their mind. Address the concern. Now, some of you are thinking, but my child needs to pass tests, needs good grades, needs to get into college. I can't ignore the system. I can answer honestly, you're right. The system exists. The system rewards memorization. You can't completely ignore it. Cran but offer the solution, but you can do both. You can help your child pass the tests while also developing their thinking. The tests require memorization. Fine, help them memorize enough to pass. But don't stop there. Don't make that the goal. Make thinking the goal. Make understanding the goal. The tests are just hoops to jump through. The real education is developing their mind. Make it concrete as your child has a biology test on photosynthesis. They need to memorize the formula. Help them do that. But also go deeper. Why does photosynthesis work this way? What would happen if it worked differently? How did plants evolve this? How does this connect to what we know about chemistry? Pass the test. But develop thinking. Don't let the test be the limit of learning. Share Feynman's own experience of Feynman did this. He passed tests. He got good grades. He succeeded in the traditional system, but his real education happened outside the tests. In exploration with his father, in figuring things out on his own, in thinking deeply beyond what was required. The tests were obstacles to overcome. The thinking was the actual education. Therex present the bigger picture, here's the bigger truth. The world is changing rapidly. When today's children enter the workforce, most jobs will be different from what they are now. Many jobs will involve problems we can't even imagine yet. Situations that require adapting, thinking, creating solutions that don't exist. Make the stakes clearer, memorization machines will be obsolete. Computers already memorize better than humans. AI already retrieves information faster than any human can. But thinkers will be invaluable. People who can reason about novel situations, who can solve undefined problems, who can think creatively, who can adapt. A direct statement, that's what your children need. Not the ability to recite facts, the ability to think, and you can give that to them. You can raise thinkers instead of memorization machines. Laser present the practical summary. Here's how apply Feynman's 5 principles. 1. Reward thinking, not just answers. Praise the process. Value good reasoning even when it's wrong. 2. Make mistakes safe. Celebrate not knowing. Treat errors as learning opportunities. 3. Ask questions instead of providing answers. Guide thinking. Don't do the thinking for them. 4. Go deep instead of covering everything. Understand thoroughly. Don't rush. 5. I've learned through experience and discovery. Create, experiment, observe. Don't just memorize. Make the promise to do these things, and you'll raise a thinker. Someone who can actually use their mind. Someone prepared for a world we can't predict. Someone capable of handling whatever challenges emerge. Tell final story. Let me end with one more story about Feynman. Late in his life, someone asks him, "What made you such an exceptional physicist? What made you able to think in ways others couldn't?" And Feynman doesn't credit his intelligence. He credits his father. Those walks in the woods, those questions, that approach to learning. Hot share his answer. My father taught me to think, not to memorize. He taught me to question, not to accept. He taught me to reason, not to recite. That's what made the difference. Not being smarter. Being a thinker instead of a memorization machine. Our final challenge, that's available to your children too. That kind of thinking. That kind of capability, that kind of preparation for the future. But only if you choose it, only if you prioritize thinking over memorization, only if you resist the pressure to create another memorization machine and instead commit to raising a thinker. The Zum walk to center. The world doesn't need more children who can recite facts. We have machines for that. The world needs children who can think, who can reason, who can solve new problems, who can create new solutions, who can adapt to unknown challenges. A direct address here, your children can be those people. If you raise them as thinkers instead of training them as memorization machines. A final statement, so make the choice. Choose thinking over memorization. Choose understanding over coverage. Choose depth over breadth. Choose questions over answers. Choose reasoning over recitation. Raise thinkers. The world needs them. Your children deserve to become them. Thank you. And if you want to understand more about Feynman's approach to education, if you want more specific techniques for developing thinking instead of memorization in children, do me a favor. Like this video and subscribe to the Mind of Richard Feynman channel. We're exploring how to actually educate for understanding and capability, not just test scores. Join us. Let's raise thinkers together. See you in the next one.
There is a lie about the double slit.
experiment that's told by everyone from famous physicists to YouTubers and even ways to believe it. The lie is, brah, hen you shoot electrons at two slits, brr. If you don't watch which way they go, brr. Cruff, they'll act like waves. But if, brr, oh, you do watch which way they went, then, brr. Hey, act like particles. They go, brah. Straight through, and they end up in 2-bar lumps. This actually contradicts the salts of the experiment, and it's completely the wrong lesson to take from he double-slit experiment. But this Lieber has been told so often that it's kind of a life of its own. The real lesson this experiment is way more interesting. And I want to tell you about that. But first, let's find out what the electrons actually do when you serve them. Because it's not this Magina. We do have a bunch of articles like this that are going to craft this double-slit experiment. You expect to have like 2 bunches of articles, and actually these slits are airy, narrow, and very close together. So, you'd kind of expect a bit of overlap between those 2 heaps. But here's what old happened for a wave. Okay, so I love his website because it's a wave emulator, and I'll link it in the description. But basically what we're owing here is we have this wall with 2 arrow slits, and we're going to see what happens when these waves go rough. So what you're seeing happen here is that there are these 2 A's coming from each of the slits. But when they touch each other, something weird happens. They interact with each other and kind of overlap. And if we let this go further, these interference patterns always kind of look like this, where there's a very strong bit of wave in the middle, and there's not much, and then there's more wave, and then again, there's a blank spot, and then another strong spot, etc. And as we saw in that simulation, what you'd expect for a wave is that it hits this back wall in this very funny pattern. There are some spots like this one where it's very intense, and then there are some spots like this where not intense at all. And there are these little bands of, intensity and no intensity. And when you do this experiment with light, that's exactly what you see, which suggests very strongly that light is a wave. In fact, the double-slit experiment was the thing that really convinced people that light is a wave after all. And I've done the double-slit experiment in a couple of videos before, and I always get a lot of comments being like, this is just classical optics, and that is true. But then they say, therefore, it's irrelevant to quantum mechanics, and that I disagree with, and I'll explain why a little bit later. But first, let's think about the same experiment with electrons. Is it going to turn out more like the particle case or more like the wave one? Well, this is footage from an actual double-slit experiment using electrons. So let's see what the answer is. Well, it's looking very promising for particles, because unlike with a wave, the result isn't just sort of smeared out. It's coming in these individual dots. But if we let the pattern develop, you start to see that it actually isn't in 2 lumps. It looks much more like the double-slit interference pattern for waves. So something really odd seems to be happening with these electrons. There seems to be some sort of wave associated with the electrons, and the wave spreads out. And just like a water wave or a light wave, it goes through both slits. The only real difference between an electron and a wave that goes through both slits is that the electron still ends up as dots. It isn't smeared out the way that waves usually are. But this feels wrong, because for something like light, it's perfectly fine to accept that it's some sort of wave. But for electrons, we're used to thinking of them as little bullets like this, little particles. And a particle couldn't be going through both of these slits at the same time. That's why it's really natural to think that if electrons really are going through both slits, then maybe let's try and catch them in the act. Let's put 2 measuring devices here and here that will watch both of these slits, and we'll tell you whether the electron actually goes through both slits. The idea is that we want to be able to catch the electrons doing both things at the same time, but measurement in quantum mechanics doesn't work like that. So in quantum mechanics, when you try and measure an object, that's in a superposition of 2 different things like this electron going through both slits, then you will see a particular result. For example, this detector might see an electron go by. But now in quantum mechanics, what happens is that measurement changed the electron. Now it's only going through one of these slits, the one you observed. So far this is all correct. But here comes the myth. Many people will tell you that now that the electron has been measured, it becomes a particle. And so this particle will act like any normal particle, will sort of end up here. And so you can imagine that if we keep measuring which way every electron goes, then you end up with two piles of electrons. People will draw the results just like this as two clumps, or at most as two overlapping clumps. And so before I ever did these experiments myself, I assumed that this is what happens. But that's not at all the case. And I'll get a curve that will probably look more or less like this. I wish I had experimental footage of someone actually doing this experiment with electrons to show you that this is not what happens, but I don't. And I also can't do this experiment myself because working with the electrons is really hard. You need like a vacuum pump and everything, but the results that you get when you do the experiment with light are very, very similar. And so I did that experiment in my previous video, and this is the result that I got. What on here? Is this crazy pattern? It doesn't look anything like two lumps. This is actually called the single slit interference pattern, and it's still very much wave behavior. Let me show you. So this is what the interference pattern looked like with the two slits here and here. But what happens if we take that away and instead just have one slit? So here I can change this from double slit to single slit, and let's see what happens. Okay, so it's much less distinct now, but you can still see some funny pattern going on here. So look, what happens at this bit where the slit is, you can see that there's like a funny sort of edge effect on both sides, and that edge, these two edges are what are going to interfere with each other. So the edges of that single slit interfere so that you get this kind of weird interference pattern. It looks quite similar to the double slit one, but just with like less fringes. So there's this bright fringe and then dark fringe and then a much less bright fringe and a dark fringe, etc. The single slit interference pattern looks something like this. But again, when we do this experiment with electrons, not actual waves, what we get is a slightly different pattern. We still get the electrons arriving in individual dots like this, but it's just that the dots are going to be according to this pattern. If you're wondering how this is different from the double slit experiment, remember that there were all these little dips inside of the bigger single slit pattern like this. So when you're not observing and you let the electrons go through both slits, then you get even more interference. But even when you just allow the electron to go through one slit by observing it, you still get a wave interference pattern. So what's going on? Well, let me tell you the correct explanation of the double slit experiment according to quantum mechanics. So for both light and for electrons, there is this thing called the wave function, which I've drawn here. It's the wave associated with that object. And when the two slits are open and not observed, the wave will go through both of those slits and interfere with itself. But in quantum mechanics, if you ever try and observe the position of an object, it can no longer be spread out like this. So when you do this observation, it forces the electron to collapse to just one of these. And so the electron acts like a wave even after it's been observed. And we know that because you end up with this single slit interference, which is just impossible to explain with purely particle behavior. If it's a wave, then shouldn't we expect a big smear across this wall rather than these individual particle-like things? Well, again, our measurement rule comes into play. In quantum mechanics, you can have an object that is spread out like a wave, but when you measure the position of that object, it's forced to collapse to a smaller position. So we have an electron that goes through here. When we measure it at the wall, it has to choose where to turn up, and it's going to be more likely to turn up in one of these bigger regions. So are electrons waves or particles? I think that even in this case where you're measuring the electron, it clearly acts in a way that's governed by this wave function. The wave is what determines what it does. But there is a sense in which it's particle-like. And that is because when it turns up on the wall, you find that there's always a full electron that turns up in any one spot. Like this electron has the same mass as that electron. So the fact that they arrive as these discrete and countable and always sort of the same size packages is what makes them particle-like. It's the fact that they can kind of be counted. And here's where it gets a bit weird. Light is exactly the same. In my previous videos about the double slit experiment with light, I got a lot of comments saying that the experiment that I was doing was just an experiment from classical optics, and all it showed is that light is a wave, which we've known for a long time. And that is all true, but I think that the quantum version of that experiment is not what people think. I got a lot of comments saying, why don't you do the single photon at a time version of this experiment? And the thing is, I would love to do that experiment, but I actually think it's going to be a little bit underwhelming, because basically this is how you would do it. Say that this is my source for the light. Then to do the single P photon at a time version of this experiment, all I need to do is to turn down this light. So I've just maybe put some filters in here that block the majority of the light. So there's only a little bit going through. Now our intuition tells us that if light is a particle, this thing called a photon, then surely it needs to be a particle like those little bullets that we were talking about. In that case, it would make total sense to talk about a single photon going through this experiment at a time. But that's not how light works. If I just put a filter in front of this laser, all I'm going to do is I'm going to make this wave weaker. From the side on view, the wave would look something like this, right? And as you put more filters in front, all that will happen is that the wave will get smaller and smaller. But no matter how many filters you put here, it's still a wave. At no point does it become a particle like this. And so you can see that no matter how weak these waves become, that doesn't stop them from spreading out like this. And the spreading is what really causes the double slit interference pattern. And so you still get the interference pattern. However, there is one really different thing about the result. Instead of getting a smear like you usually do with a double slit experiment, you're going to find actually the light arrives in little dots just like the electrons. But how is that possible? I said that nothing really changed when you turn down the intensity of this light. Well, the thing is, when we have this light at full brightness, there are individual dots turning up here, but we can't see them because there's so many coming per second that it does just look like a smear. And it's only by turning down the light that we end up seeing these individual photons. So photons are particles much like electrons are particles. They're not really, they're more waves. But a photon or an electron is more a property of what happens when they get measured. Whenever you have a quantum wave function like this and you try and measure the position of that object, it's forced to collapse to one particular spot. After I finished recording, I found out that there's this amazing paper where they explain how you can see the individual photons of light arriving. It is from 2016, and I'll link this in the description, but here's the video. So as you can see here, there are these individual photons, and it kind of looks random at first, but you can already start to see how it seems to be gathering around these fringes, which is exactly what you would expect for a double slit experiment. I'd seen this experiment with electrons before, but it was very cool to see it with photons. And as you can see, the two experiments look nearly identical. Another way that photons are very like electrons is that each individual photon has the same amount of energy as the other. Just like with electrons, they come in these discrete packages that are always of the same size. So for both electrons and photons, they don't really exist as particles. Throughout this part of the experiment, they only really become particles here when they're measured. But then you might wonder, how can we even talk about doing this experiment one photon at a time? Well, the way that you do it is you kind of turn down this light a whole lot so that there's only a few of these photons coming, let's say, every second. And it takes much less than a second for any light to have gone from the source all the way to the wall. And so you kind of say, well, that means that there couldn't have been more than one photon sort of going through this whole thing at a time. So that's a one photon at a time experiment. And I think that just is bad terminology. Like, there are no photons, really, until you get to here. For both electrons and photons, we imagine these as sort of individual balls coming out of the source. And that's what's the source of the confusion, because we think that a single particle can't go through two slits at the same time. But there is no contradiction when you see that both of them are actually just waves. And waves absolutely can go through both slits at the same time. They really only become particles when they're measured at the wall. That's why I think that experiments with light are still very interesting quantum mechanically, because we know from the maths of quantum mechanics that light and electrons behave almost identically. Like in my last video where I did the quantum eraser experiment with light, and it was very easy, and it just involved polarizers. A lot of people pointed out that you can totally explain this just using the regular polarization of light in classical optics. But did you know that you could do that exact same experiment again using the spin of the...
Ladies and gentlemen, let me start with a word we all think we understand: energy. We use it constantly. We drink it in cans. We complain about not having enough of it. We talk about good energy, bad energy, and saving energy. And yet, despite how familiar the word feels, energy is one of the most misunderstood ideas in all of science. Tonight, I want to do something very simple and very dangerous. I want to take that word away from you and then give it back in a form that actually makes sense. Here's the first thing you must accept. Energy is not a thing. You can't touch it, you can't see it, you can't put it in a box. If you try to imagine energy as a substance, some invisible fluid sloshing around the universe, you will be confused for the rest of your life. Energy is not stuff. Energy is a number, a bookkeeping number. And that fact alone already tells us something profound about how the universe works. Now, this sounds disappointing at first. A number, that's it? Yes and no. Because this number has a remarkable property. It never changes. No matter what happens, collisions, explosions, chemical reactions, stars being born, stars dying, the total amount of energy stays the same, always, every time. The universe keeps perfect accounts. This principle is called the conservation of energy, and it is one of the deepest truths we know about nature. Not because we proved it, but because every experiment we've ever done has failed to contradict it. Nature could have chosen otherwise. It didn't. Now, here's where things get interesting. If energy is just a number, what does it count? It counts the capacity for change. Any time something happens, anything at all, energy is involved. Motion, heat, light, chemical reactions, life, thought. If something can cause something else to happen, energy is keeping score. Think of energy like money. Money isn't a thing either. It's an accounting system that tracks the ability to make changes in the world. You can store it, transfer it, convert it, waste it. But the money itself doesn't do anything. People do. Energy works the same way. Now let me ruin another comforting idea. Energy does not come in just one form. We give it names: kinetic energy, potential energy, thermal energy, chemical energy, mass energy. But these are not different substances. They are different ways the same number appears, depending on the situation. Like the same amount of money appearing as cash, credit, or investments. Different forms, same total. Here's the rule the universe follows. Energy can change its form, but it cannot disappear, ever. When energy seems to vanish, it hasn't. It's just gone somewhere less useful, usually into heat, the universe's junk drawer. Now pause and think about this. Every machine ever built, every engine, every living organism, every civilization, all of it is about moving energy from one form to another. Life itself is not about creating energy. It's about channeling it cleverly. And here's the twist most people miss. Energy is not conserved because of some mechanical rule. It's conserved because the laws of physics do not change with time. The universe today follows the same rules it did yesterday. That symmetry, time behaving consistently, is what protects energy. Energy conservation is not just a rule, it's a consequence of order. This means something extraordinary. If tomorrow the laws of physics change slightly, energy would no longer be conserved. The universe would become unpredictable, chaotic, unrecognizable. The fact that energy is conserved tells us that reality has a deep underlying stability. But now we must confront the most unsettling idea of all. If energy is always conserved, and everything that happens uses energy, where did it all come from? And even more troubling, what does it mean that you are part of that accounting system?
To answer that properly, we need a concrete handle, something ordinary, familiar, almost boring, because energy only becomes confusing when we talk about it abstractly. When we watch it work, the mystery sharpens. So, let's start with a machine so simple it feels harmless. Imagine a pendulum, a weight on a string. You lift it, let it go, and it swings back and forth. Nothing dramatic, no smoke, no sparks, no equations carved into stone tablets. Now here's the question your intuition answers instantly and incorrectly. You look at the pendulum and think. At the top, it has potential energy. At the bottom, it has kinetic energy. They trade places. That story feels satisfying. It feels like something is moving around inside the pendulum, but nothing is moving except the pendulum itself. The energy isn't hiding somewhere, waiting its turn. There is no little packet labeled potential that jumps into a packet labeled kinetic. What's actually happening is much stranger. At the top of the swing, the pendulum is arranged in a way that could cause motion. At the bottom, it is arranged in a way that is motion. Energy isn't a thing passing back and forth. Energy is a number that stays the same while the description changes. Same system, same total, different bookkeeping. Now let's push this further, because common sense is still clinging on. If energy is conserved so perfectly, the pendulum should swing forever. But it doesn't. It slows. It stops. Eventually it just hangs there doing nothing. So where did the energy go? You already know the answer. Friction, air resistance, heat. But notice what your intuition tries to sneak in. It imagines energy leaking out like water from a cracked pipe. That's wrong. Nothing leaked. The energy is still there, just spread out among too many atoms to be useful anymore. The air warmed slightly. The pivot warmed slightly. The earth warmed slightly. The universe noticed. You didn't. This is the moment where common sense fails most dramatically, because common sense equates not useful with gone. Physics does not. Physics only asks one question: can I still account for it? And the answer is always yes. This was made brutally clear in a famous 19th century experiment by James Joule. Joule took a container of water, dropped weights that turned paddles inside it, and measured the temperature increase. Mechanical motion turned into heat, not metaphorically, not symbolically, quantitatively. Drop the weights twice as far, the water heats twice as much. Every time, no exceptions. Energy didn't vanish, it changed what it was doing. This is the core mechanism you must understand. Energy does not care what it looks like. It only cares that the total is preserved. Motion, heat, light, chemical bonds, electrical currents, these are not different substances. They are different languages describing the same constraint. Now let's challenge intuition directly. You feel tired. You say, I'm out of energy. But that's false. You are full of energy. What you lack is accessible energy in a useful form. Your body is a chemical engine. It runs by converting tightly packed chemical energy into motion, heat, and electrical signals. When that conversion becomes inefficient, you feel exhausted, not because energy is gone, but because it's trapped in forms your muscles can't use quickly. The universe didn't take anything from you. It just made conversion harder. This is why engines matter so much in physics. A steam engine, a car engine, a cell, these are not energy creators. They are energy translators. And translation is never perfect. Some meaning is always lost. Some energy always ends up as heat. That's not poor engineering. That's reality. Here's the analogy that usually snaps things into focus. Imagine energy as money, but money that can only be spent in certain stores. You might be incredibly wealthy, but if all your money is locked in a currency no one accepts, you're powerless. Energy works the same way. The universe accepts fewer and fewer currencies over time. And now comes the realization that unsettles people. The conservation of energy is not about motion or machines. It's about consistency. The universe does not change the rules halfway through the calculation. If you run an experiment today or 1 billion years ago, the accounting balances the same way. Energy conservation is not enforced by a cosmic police officer. It happens because the laws of physics are stable in time. If the rules drifted, even slightly, energy would not be conserved, and neither would anything else you rely on.
So when common sense says energy makes things happen, physics quietly corrects it. Energy does not cause change. Energy measures the capacity for change under fixed rules. The rules come first. Energy keeps score. This is why energy feels so fundamental. It's not because it's a substance beneath everything. It's because every possible change must respect it. No loopholes, no exceptions, no negotiations. And that brings us back to you. You don't sit outside this process observing energy flow through the universe. You are one of the allowed pathways energy discovered, a pattern that holds for now. And once you see that, once you really accept that energy is not a thing, but a rule you can't cheat, something subtle happens. The universe starts to look less like a collection of objects and more like a collection of allowed changes. Because energy doesn't tell matter what to do. It tells matter what it is not allowed to do. You can rearrange endlessly, but you must always balance the books. This has consequences that reach far beyond engines and machines. For example, motion. We tend to think of motion as primary, as something basic, things just move. But motion turns out to be negotiable. You can always change your point of view and make a moving object look still. You can ride alongside it. You can redefine your frame. Energy doesn't care. The energy accounting works in every frame, every perspective. That's already a hint that energy is deeper than motion itself. Now let's talk about forces. Forces feel real. You feel gravity. You feel a push. You feel resistance. But forces are not fundamental in the way we instinctively think. A force is just a way of describing how energy changes with position. That's it. If energy depends on where something is, it experiences a force. No mystery, no hidden hands, just bookkeeping again. The universe doesn't push things, it follows gradients in energy. This quietly unifies an enormous amount of physics, gravity, electricity, magnetism, even the forces inside atoms. They all emerge from the same idea, energy arranged differently in space and time. Once you see that, the laws of physics stop looking like a random list of rules and start looking like variations on a single theme. Now here's where the surprise enters. If energy is always conserved, and if it controls what changes are allowed, then energy places limits on reality.
absolute limits. You cannot build a perpetual motion machine. You cannot extract infinite work. You cannot rewind the universe to yesterday, not because we lack cleverness, but because the rules don't allow it. This is where physics becomes philosophical, not by adding speculation, but by refusing to. The universe is not just what happens, it is what is permitted to happen, and energy is one of the strictest permissions we know. This brings us to a paradox people often stumble over. If energy is conserved so perfectly, how can anything genuinely new ever occur? How can novelty exist if the total never changes? It feels like a contradiction, but it isn't, because novelty doesn't come from new energy, it comes from new arrangements. The alphabet is finite, the number of books is not. This is why complexity is possible. Stars, planets, life, minds, none of these required extra energy to appear. They required pathways, sequences of transformations that happened to hold together long enough to build structure. Energy didn't create complexity, energy allowed complexity. And now let's confront something even more unsettling. If energy accounting governs everything, then causality itself is constrained by it. You can't get an effect without paying the energy cost. You can't get information without dissipation. You can't think without burning fuel. Every thought you've ever had has a thermodynamic footprint. Meaning is not free. Understanding is not free. Awareness is not free. They all cost energy. This doesn't diminish them, it grounds them. It tells us that meaning is not an exception to the universe, it's one of its natural outcomes. At this point, people often ask, so is energy the most fundamental thing? And the honest answer, the only respectable answer is, we don't know. Energy may be fundamental, or it may be a shadow of something deeper, the way temperature is a shadow of molecular motion. What we do know is this: any deeper theory we find must still explain why energy accounting works so perfectly, because reality refuses to let us escape it. And notice something remarkable. We never defined energy by what it is. We defined it by what it does. It constrains, it balances, it limits, it connects. Energy is less like a substance and more like a promise the universe never breaks.
This changes the meaning of understanding. To understand something deeply in physics is not to imagine it vividly. It is to know what cannot happen, no matter how much you want it to. That's real knowledge. So when you ask what energy means, the answer is not poetic, but it is profound. Energy means the universe is consistent. Change is possible, but not arbitrary. Complexity can arise without miracles, and nothing gets a free pass. So now we can finally assemble the whole picture, not as a collection of clever ideas, but as a single working view of the world. Energy, at the deepest level we currently understand, is not a material ingredient added to the universe. It is a constraint on change. It is the quantity that must remain constant, no matter how wildly the universe rearranges itself. Every law we trust, every equation that survives experiment, respects that constraint. This already tells us something concrete and non-negotiable. The universe is not free to do just anything. If a process violates energy conservation, it does not merely seem unlikely, it does not exist. Full stop. This is why physicists take energy conservation more seriously than almost any other principle. Entire theories have been discarded, not because they were inelegant, but because they failed to conserve energy. Even relativity and quantum mechanics, radical as they are, were built to preserve it, not replace it. We also know something very specific about why energy is conserved. In modern physics, conservation of energy arises from a deep symmetry.
The laws of physics do not change with time. An experiment performed today will behave the same way tomorrow or 1 billion years from now. That temporal stability is not an assumption. It's an observed fact, tested constantly. If the laws of physics drifted even slightly with time, energy would not be conserved. The universe would gain or lose energy without explanation. The fact that this does not happen tells us that time itself has a remarkable uniformity built into it. That is not philosophy. That is measurement. Now let's be precise about what energy actually tracks. Energy is not a cause. It is not a force. It is not an agent. Energy is a scalar quantity that assigns a value to the state of a system. That value determines which changes are allowed and which are forbidden. Systems naturally evolve toward states where energy is more evenly distributed, because those states are overwhelmingly more probable. This is why heat flows from hot to cold, why friction exists, why engines have efficiency limits, why time has a direction. Not because the universe prefers disorder, but because there are simply more ways for energy to be spread out than concentrated. We also know something else that matters enormously. Energy conservation does not mean nothing truly happens. It means nothing happens for free. Every increase in structure requires energy to be concentrated somewhere, and that concentration must be paid for by dispersing energy elsewhere. This is why every act of creation is also an act of waste. Every star, every organism, every idea is accompanied by heat leaking into the surrounding universe. Life does not violate this rule. Life survives because it obeys it more cleverly than its surroundings. Now, what don't we know? We do not know why the universe began in a state where energy gradients existed at all. We do not know why there was something like usable energy instead of a perfectly uniform, inert equilibrium. We do not yet know whether total energy of the universe is exactly zero, positive, or even definable in a simple way at cosmic scales. We also do not know whether energy is truly fundamental, or whether it emerges from a deeper description, perhaps one based on information, geometry, or quantum structure. These are open questions, real ones, active ones. Energy conservation is not the final word. It is the rule that every deeper theory must still explain. And now, here is the synthesis that matters. Energy tells us that the universe is not arbitrary. It is constrained, consistent, and legible. It tells us that change is possible, but only along permitted paths. It tells us why complexity can arise without miracles, and why permanence is never guaranteed. And most importantly, it tells us something about our place in the story. You are not an exception to physics. You are not outside its accounting. Your metabolism, your memory, your thinking, all are physical processes with measurable energy costs. Thought consumes fuel. Learning leaves thermodynamic traces. Meaning requires work. That does not reduce human experience. It anchors it.
The final takeaway is not that energy explains everything. It's that energy explains why explanations work. Because the universe keeps its books honestly, patterns can persist, laws can be discovered, and understanding can multiply. Without that consistency, science itself would be impossible. Energy is the quiet agreement reality makes with itself. Change is allowed, but it must balance. And because of that agreement, there is motion, time, life, curiosity, and the universe capable of being understood at all.
You think you understand gravity? Step on a scale. See the number. That's your weight. Earth pulling you down. Simple. Drop something, it falls. Moon orbits Earth. Planets circle the sun. Objects with mass attract each other. Newton figured it out centuries ago. The so-called force of gravity seems easy to understand. Simple even. Wrong. Not a little bit wrong. Fundamentally wrong about what's actually happening. Because gravity isn't a force at all. And when you finally see what gravity really is, when you really see it, the whole universe starts to look different. Let me show you. Stand up right now. Feel your weight. What are you feeling? You say, gravity, earth pulling you down. But think about the actual sensation. The floor pressing against your feet, pushing up. That's what you feel. The floor pushing. This mysterious pull everyone talks about, you never feel it, not once. You only feel the push, always pushing up, never pulling down. So where's this pull? And here's something stranger. The moon is falling toward Earth right now, has been falling for billions of years, but it never gets closer, just circles, always falling, never landing. What kind of pull works like that? A pull that pulls forever, but never pulls anything in. And according to Newton, that pull happens instantly. Move Earth and the moon feels it immediately across 240,000 miles of vacuum, instantly. How? What carries the message? What's the mechanism? Newton himself couldn't explain it. He called it action at a distance and admitted he didn't understand how it worked. But the mathematics was beautiful. The predictions were perfect. So people stopped asking uncomfortable questions. They shouldn't have stopped. Go back several centuries. Nobody understood how planets moved. Copernicus said they orbit the sun. Fine. But how? What paths do they follow? Tycho Brahe built an observatory and spent decades recording planetary positions, night after night, year after year, measuring angles with brass instruments to fractions of a degree. Why such precision? Because you can't understand nature by guessing. You have to look. Measure carefully. Write down exactly what you see. That's where real science begins. His data reached Johannes Kepler. Kepler wanted to find the shape of planetary orbits. He tried circles. The predictions were close, but Mars was off by 8 arc minutes, 8/60ths of a degree. Most people would shrug that off as measurement error, but Kepler knew Tycho's precision. That man didn't make 8 arc minute errors. So Kepler threw out his theory and started over. After years of work, he found it. Ellipses. Planets move in ellipses, with the sun at one focus. Perfect match to the data. Beautiful. But it raised a bigger question. Why ellipses? Meanwhile, Galileo was doing simple experiments, rolling balls down ramps. Sounds trivial, but watch what happens. Roll a ball down an incline. It speeds up. Let it roll onto a flat surface. It keeps going, doesn't stop immediately. Now imagine you could eliminate all friction. What would happen? The ball would roll forever. Same speed, same direction, forever. This bothered people. Surely motion requires a continuous push. Surely things naturally come to rest. No, that's backwards. Motion is natural. An object moving in a straight line doesn't need explanation. That's the default state. What needs explanation is change. Slowing down, that's friction. Speeding up, that's a push. Changing direction, that's a sideways force. This is inertia, the first law of motion, and it creates a puzzle. Planets should move in straight lines. That's their natural state, but they don't. They curve. Their paths bend continuously toward the sun. Something must be deflecting them every instant. What? Isaac Newton saw it clearly. Planets want to go straight. That's inertia. But they curve. Something changes their motion constantly. He called it gravity. Universal attraction between any two masses. The force depends on mass and distance. More mass means stronger force. Greater distance means weaker force. Specifically, force drops with the square of distance. With this one principle, everything fell into place. Why ellipses? because planets are falling toward the sun while simultaneously moving sideways. The combination creates elliptical paths. Kepler's laws emerge naturally from Newton's force law combined with inertia. Why does the moon orbit Earth? Same principle. It's falling toward Earth, but moving sideways fast enough to keep missing. It falls around Earth instead of into it. Why does an apple fall? Earth attracts it. Same force, same law, just different scale. Newton did a beautiful calculation. He figured out how much the moon falls every second, how much its path deviates from a straight line. Then he calculated how much objects fall on Earth's surface. The numbers matched perfectly when accounting for distance. Revolutionary. The force pulling an apple is the same force holding the moon in orbit. Heaven and earth, same physics. With Newton's law, everything made sense. Ocean tides happen because the moon pulls on Earth's water. Earth is round but bulges at the equator because it spins. Comets return on predictable schedules because they follow elliptical orbits. Strange observations found explanations. Jupiter's moon sometimes appeared early, sometimes late. Turned out light takes time to travel. When Earth is farther from Jupiter, light takes longer to reach us. This led to measuring light speed for the first time. Planets wobble slightly because they pull on each other, not just on the sun. From the wobbles in Uranus's orbit, astronomers predicted a new planet, Neptune, and found it exactly where predicted. For 2 centuries, Newton's law of gravity stood as one of the greatest achievements in science. It explained everything anyone could measure, but there was one detail nobody could explain. Drop a hammer and a feather in a vacuum. They hit the ground at the same time, exactly together. The hammer has more mass. So according to Newton, gravity pulls it harder, much harder. But the hammer also has more inertia. It resists acceleration more, much more. These 2 effects cancel perfectly, not approximately, perfectly. Every object falls at the same rate regardless of mass. Why? Newton's theory requires 2 different properties of mass. Gravitational mass determines how strongly objects attract each other. Inertial mass determines how hard it is to accelerate something. And these 2 properties are always perfectly proportional for every substance ever tested, to incredible precision. But why should the attracting property of mass and the resisting acceleration property be perfectly equal? Newton had no answer, just a remarkable coincidence that made the mathematics work beautifully. Or was it a coincidence? Einstein asked a different question. What if it's not a coincidence? What if that perfect equality is telling us something fundamental about what gravity really is? Here's a thought experiment. You're in a closed room with no windows. You feel your normal weight pressing you to the floor. Are you on Earth, or are you in a rocket in deep space, accelerating upward at 9.8 meters per second squared? Can you tell the difference? Drop something. It falls to the floor in both cases. Throw a ball horizontally, curved path in both cases. Stand on a scale, same reading in both cases. There is no experiment that can distinguish them. This is the equivalence principle. If you truly cannot tell gravity from acceleration, maybe they're the same thing. Maybe what we call sitting still in a gravitational field is actually a form of acceleration. Here's Einstein's revolution. Objects in free fall have no force acting on them. The falling apple, the orbiting moon, satellites circling Earth, astronauts floating in space capsules. None of them experience any force. They're moving naturally, following their natural paths. No forces, no pulls, nothing acting on them. But the apple is clearly falling. Yes, but what if the apple isn't accelerating at all? What if it's following the straightest possible path and it's space itself that's curved? This is Einstein's profound insight. Gravity is not a force between objects. Gravity is the curvature of space and time. Massive objects don't pull on other objects. They warp the space around them. They bend it, curve it, distort the geometry. The apple isn't being pulled to the ground. It's following the straightest possible path through curved space-time. But space-time near Earth is curved, so straight points toward Earth's center. You standing on the ground aren't being pulled down. You're trying to follow your natural path through curved space-time, a path toward Earth's center. But the ground is in your way. The ground pushes you upward, preventing you from following that natural path. That's what you feel as weight, not gravity pulling down. The ground pushing up, deflecting you from your natural trajectory through curved space-time. Einstein made a concrete prediction. If gravity is really curved space-time, then light should be affected too. Light has no mass. In Newton's theory, gravity shouldn't affect light at all. But if gravity is curvature of space itself, then light following the straightest path through curved space should bend. During a solar eclipse, astronomers measured the positions of stars near the sun's edge. The stars appeared displaced from their true positions. The starlight had bent, passing near the sun, exactly as Einstein predicted. This is gravitational lensing. We see it in observations all the time now. Massive objects bend light from more distant objects behind them, creating distorted images. Direct evidence that space itself curves in the presence of mass. Astronauts in orbit look weightless, floating around. Zero gravity up there, right? Wrong. The gravitational field at the altitude of satellites, a couple hundred miles up, is almost as strong as here on Earth's surface, about 90% as strong. So why do astronauts float? Because they're falling. The capsule is falling. Everything is falling toward Earth constantly. But they're also moving sideways very fast, about 17,000 miles per hour. As they fall, Earth's curved surface falls away beneath them. They keep missing. They fall around Earth instead of into it. Everything falls together at exactly the same rate. So there's no sensation of falling, no weight, no sense of up or down. It feels exactly like floating in empty space, far from any mass. This is equivalence in action. Free fall in a gravitational field feels identical to floating freely in empty space because they are the same thing. In free fall, no force acts on you. You're following the natural geometry of curved space-time. Think of Earth's surface. It's curved, but standing on it, it looks flat to you. And here's something remarkable. Why is Earth round in the first place? Because of gravity, but not in the way you think. It's not that some force is pulling everything toward the center, molding Earth into a sphere. It's that space-time around Earth's mass is curved equally in all directions. Every piece of rock, every drop of water is trying to follow the straightest path through that curved geometry. And when everything follows those curves from all directions equally, you get a sphere. The only shape where every point on the surface is the same distance from the center. Earth is round because that's what happens when matter follows curved space-time. The shape emerges naturally from the geometry. An ant walking what it thinks is a straight line on that curved surface actually follows a curve. But from the ant's perspective, it's going perfectly straight. That's what's happening with everything near Earth, except it's not just space that's curved, it's space and time together, space-time. Massive objects create curves in space-time, depressions, wells, distortions. The sun creates a deep well. Earth creates a smaller one. Even you create a tiny well, too small to measure easily, but it's there. Objects moving near these wells naturally follow the curves, not because anything pulls them, because they're following the straightest possible paths through curved geometry. The moon orbits Earth because it's following the natural geometry of curved space around Earth. That geometry makes the straightest path into a circle. An apple falls because it's following curved space-time near Earth's surface. In that curved geometry, straight ahead through time points toward Earth's center. When you throw a ball, it follows a parabola, not because gravity pulls it down, because it's moving through curved space-time, and the straight line in that curved space looks like a curve to you. You're standing right now. You feel weight. In Newton's picture, gravity pulls you down and the floor pushes you up. Two forces balanced. In Einstein's picture, only one force acts on you, the floor pushing up. But if there's only one force, you should be accelerating, and you are. You're accelerating upward constantly. The natural path through space-time points toward Earth's center. That's the free fall trajectory. But the floor is in your way. It pushes you upward, deflecting you from that natural path. You're like someone standing in an accelerating rocket. The floor pushes. You feel weight, not from any downward pulling force, from being accelerated away from your natural path. The apple hanging in a tree is also being pushed upward by the branch. When the branch breaks, the pushing stops. The apple is suddenly free to follow its natural path through curved space-time. It falls, but the apple isn't accelerating. The apple is finally free to move naturally. You standing on the ground are being constantly accelerated upward by the floor pressing against your feet. Falling is the natural state. Standing still requires a force. That's Einstein's revolution. Once you understand gravity as geometry, extreme phenomena make sense. A star is essentially a massive ball of gas. Its mass creates a deep well in space-time. The natural paths in that curved space point inward. What prevents collapse? Pressure from nuclear reactions in the core pushing outward. Balance. When the nuclear fuel runs out, the pressure drops. Balance breaks. The star collapses. If the star is massive enough, the collapse continues until matter is compressed to incredible density. Atomic nuclei merge. Electrons are crushed. What emerges is a neutron star. Nuclear matter compressed to city size. A teaspoon of this stuff would weigh 1 billion tons. For even more massive stars, not even neutron pressure can stop the collapse. Space-time curves so sharply that all possible paths lead inward. Even light cannot escape. This is a black hole. Near a black hole, space-time is so severely warped that light itself, following the straightest possible paths through this geometry, spirals inward and never comes out. We can't see black holes directly, but we see their effects. Matter falling toward a black hole speeds up, heats up, radiates enormous energy before disappearing. All from one idea. Mass curves space-time. Objects follow the curves. From this one principle, everything follows. Planetary orbits, tides, the precession of Mercury's perihelion, a tiny effect Newton's theory couldn't explain, but Einstein's predicts perfectly. Gravitational lensing, black holes, gravitational waves rippling through space when massive objects collide. The same principle explaining how the moon orbits also explains the largest structures we observe. Galaxies, clusters of galaxies, universal, elegant. The pattern in the small piece reveals the design of the whole fabric. Newton's equations work beautifully for practical purposes. We use them to launch satellites, calculate orbits, predict eclipses. They're simpler than Einstein's equations and accurate enough for most applications. But Einstein revealed what gravity actually is. Not a mysterious force pulling objects together across empty space. The curvature of space and time themselves. Mass tells space how to curve. Curved space tells objects how to move. When you step on that scale, you're not measuring a downward pull. You're measuring how hard the scale must push to prevent you from following your natural path through curved space-time. When you watch something fall, you're seeing an object finally free to follow the geometry that mass has woven into the fabric of reality. When you look at the moon, you're seeing an object following the straightest possible path through the curved space around Earth, a path that looks like a circle because space itself is curved. Space brings objects together. That's what we call gravity, not a force, geometry. And that is far more beautiful than any mysterious pull could ever be.